Hello everyone, welcome to this lecture. In our previous lectures, we've learned about how to make inference about population proportion. The first one that we have seen was how to find the estimate of the population proportion p hat. And then we learned how to make inference about one population proportion using confidence interval and hypothesis testing. And we know that it's given by p hat plus or minus the margin of error, which was given by the critical value. Well, this is z critical value times the standard deviation of p hat. And then we learned how to perform a hypothesis test about one population proportion. And later in the next, we learned confidence interval for the difference of two population proportions, and that was for p hat plus or minus p hat 1 minus p hat 2 plus or minus the margin of error of p hat 1 minus p hat 2. And then we learned how to perform a hypothesis test about this population difference of two population proportions. So this was all about population proportion for one proportion, and then for the difference of two population sample proportions. Okay, using sample proportions, we would infer about the population proportion. And today we are going to learn the constructing confidence interval about population mean. Okay, now we're not gonna it's gonna be the p is gonna be replaced by mu, so we will learn about mu. But first we need to know the sampling distribution, because first what we did was we studied the sampling distribution of p hat, and we said when the conditions are met, when np and q 1 minus p times n, they were both greater than 10, and if the sample was selected randomly, or if it is representative, then we were saying this p hat is normally distributed, right? That was the sampling distribution of p hat. And similarly for the mean x bar, for the population mean, here we have the notations. N represents the sample size, and x bar is the mean of the sample. S is the standard deviation of the sample. Mu is mean of the entire population, and sigma is the standard deviation of the entire population. So x bar is the estimator of mu. Okay, if we don't know mu, we will use x bar to estimate this one. So this is called the point estimate because it's a single number and it's used to estimate this number, but it may or may not be close to mu. Okay, we don't always get close value, right? Because there is sampling variability or sampling error. So the best way to do this is using confidence interval or hypothesis testing, and we will come to that in a bit. Now, the general properties of sampling distribution for x bar are, suppose x bar is denoted the mean of the observations in a random sample of size n from a population with mean mu and standard deviation sigma. So we're assuming, let's say this is our population, and the population has mean mu and standard deviation sigma. So these are the characteristics of this population. So it doesn't mean we know them. Of course, we don't know them. That's why we are trying to estimate this one. Okay, but This is just a variable, not a variable actually, but this is something that we are trying to estimate. The mean value of the sampling distribution of X bar is written as mu X bar. Now what we are doing here is select different samples of the same sample size from this one randomly, okay? And keep doing this. And well, hypothetically, let's collect all the samples possible to be drawn from this population. Then the X bar, all the X bars, calculate X bar from each of this sample. Let's call them X bar 1, X bar 2, X bar 3, and so on and so forth. Now find the mean of these ones. If you find the mean of this X bars, then call that one mu X bar. This is mean of the X bar. Okay, this is sub indices. And this is equal to mu, which is the actual population mean here. Okay, so average of all these means will be the same with this one. That's what we are saying here. And also the standard deviation of those means denoted by sigma sub X bar is given by sigma over root n. This n is the size of this sample, and the sigma is this sigma, okay, the standard deviation of the population. So these are the characteristics of the sampling distribution of X bar. Okay. And this is this rule is exact if the population is finite. If we have a finite population, this is exact. We get exactly like this one. Is not an estimate. And it's approximately correct if the population is finite and no more than 10% of the population is included in the sample. Okay. If you remember, we had this in estimating population proportion. It's always a good idea to include less than 10% of the population proportion, and this is one reason. And when the population distribution is normal, now suppose this the population data is distributed normally, then the sampling distribution of X bar is also normal for any sample size n. Now, if we assume this, data is normally distributed, and then these X bars, if you put them, for example, into a histogram, then it will be normal as well. It doesn't matter what sample size you take here. Okay, here we have the sample size. So it doesn't matter what sample size. It could be small or it could be large, but still you will have a normal distributed X bars. But what if this original data was not normally distributed? Well, now we need to have this restriction. We need to have a large sample. Okay, instead of n to be any number, we need n to be large. And by large here, we mean greater than or equal to 30. Okay, so if it is greater than 30, we would say n is large. Okay, well, of course, as it goes up, then it gets better and better in order to have a more symmetric and bell-shaped distribution. So when n is large, the sampling distribution of X bar is well approximated by a normal curve, and even when the population distribution is not normal. Okay, if we notice this one, we don't even care about the original distribution of the data. Even if it's not, if it is not normal, then this central limit theorem, this is a very important theorem in statistics. This theorem tells us that the when n is large, then the sampling distribution of X bar is approximately always normal. it doesn't matter whether this is normal or not. All right, so based on these rules, if n is large or if the population distribution is normal, then the standardized variable z equals to x bar minus mu x bar, this is the mean of the x bars, over standard deviation of the x bars, which is given by this one. Standard deviation of x bar is given by this, and mean of x bar is given by this. So this is approximately standardized normal distribution, okay, or standard normal distribution. When we say standard normal distribution, this has mean 0 and standard deviation mu z is 0, standard deviation of z is 1. This is what we call standard normal distribution. So now here, don't forget to include this one, because the standard deviation of x bar is sigma over root n. It's not only sigma. And the central limit theorem can safely be applied if n is greater than 30. As I mentioned earlier, we want n to be large, which means it should be greater than 30. Well, this is just a summary. Okay. And now let's start how to make inference about the population mean. So in order to make inference about the population mean, well, we've studied the sampling distribution of x bar, and we said when n is large, the distribution of this one will be approximately normal, or if the population data is normally distributed, then it doesn't matter what n we take, the distribution of this one will be normal approximately. So as we remember, the general form of the confidence interval estimate is given by this one. You have the statistic plus or minus, you have the critical value, and then you have the standard error of the statistic. Now, we will put this one in two different cases. One is when sigma is known, okay? Suppose we know sigma. Now, think of this. If we're thinking about a bigger population, so when we do, in order to do this inference, you have to do a study. You have to do a survey. You have to do the experiment. You have to do different ways, any type of collecting data. So from the when you collect data from this population, you don't know mu. That's why we are making inference. And most of the time, we don't know sigma as well. Okay, because there are population values. If I know this one, there is high possibility that I know this one. But there are some cases that from previous study, you can approximate this one. You can have an idea about what the value of this one could be. So in that case, we would say we know sigma, but in most scenarios, we don't know sigma. But now, for the sake of the theory, let's split this explanation into two. The first case is when we know sigma, how do we make inference? All right. Now, if sigma is known, the sampling distribution of x bar is centered at mu. So x bar is an unbiased statistic for estimating mean because, well, we have this one. We know this one, mu, x bar is mu. And we are saying the distribution is approximately normal. And so the distribution or the curve is centered at mu x bar, which is just mu. And the standard deviation of x bar is given by this one, because now we know sigma. So the standard deviation of x bars will be given by the population sigma divided by root n. And as long as n is large, which means greater than 30, the sampling distribution of X bar is approximately normal, even when the population distribution itself is not normal. Okay, whether it's normal or not normal, always if you have a large n, then you make sure that the sampling distribution will be normal. But if n is less than 30, what you need to check is that whether the population data or the population distribution was normal or not. Okay, if n is small, you need to know if population distribution was normal or not. If it was not normal, then I cannot say this mean or sample mean has approximately normal distribution. Like, we cannot say that. But if the population distribution was normal, then we can say that. Okay, we can say the sampling distribution of X bar is normal. Okay, now based on this, the confidence interval for a population mean when the sample size is large and sigma is known will be given by X bar plus or minus Z critical value, the same critical value that we have been using for population proportion, times the standard deviation of X bar. This is the standard deviation of X bar, which is given by sigma over root n. Okay, and remember, as a whole, this part we call it the margin of error. Okay, and usually we would use M or sometimes ME, but I think we will see in, but if I'm not wrong, we use our textbook use this M. All right, now let's look at this example. So here we have n equals to 30, and the mean here is the mean, mu is the mean annual cosmetic radiation exposure for all flight crew members. Suppose sigma is known to be 0.35 MSV. Now, as you can see n is 100, and it means it's large because this is greater than 30, and sigma is known. So 95% confidence interval for mu is given by X bar plus or minus Z critical value times sigma over root n. So for this confidence interval, the critical value, if you remember, is 1.96. Using technology, you can find this one using technology or from using the table. So we will use this same critical value. And there was this empirical rule which says 95%, 6895, and 99.7 rule. So it says 95% of the data is within 2 standard deviations. So based on that, Z will be 2. The critical value will be 2, but still it's okay even if you use this one. It's okay, but here, in order to be more precise, we will use 1.96. All right. So X bar is 3.07 plus or minus. This is the critical value, and this is the standard deviation. The numerator is the standard deviation of the population, and the denominator is square root of n. And well, this is 3.001, between 3.001 to 3.139. So that's the confidence interval for the population mu. So based on this sample, plausible values of mu, the mean annual cosmetic radiation exposure for all flight crew members are those between this value and this value. Okay, approximately, we are 95% sure that the population mean is between these two values. Okay, now how about when we don't know sigma? Okay, how do we construct a confidence interval for population mean? Or what is the difference? Where are we looking at this separately? Well, the answer is, well, if we don't know sigma, there are two things that we need to change in the formula. Okay, the formula x bar plus or minus z critical value times sigma over root n. Okay, this was the formula. Now, if we don't know sigma, I cannot use this sigma because we are saying it's unknown. And another thing is, if we don't know sigma, can we use this critical value? Okay, will the distribution of x bar be still normal? Because this is always with normal distribution. So will the distribution be normal if sigma is unknown? Okay. Well, here we have critical value is no longer based on z distribution. Okay. Well, not z distribution, but normal distribution. Okay. So here we cannot use the z critical value anymore if sigma is unknown. What do we use then? Well, we have to use a different distribution, which is called the t distribution. So if the population distribution is at least approximately normal, or if the sample size is large and greater than 30, then the critical value that should be used is based on a probability distribution called the t distribution. So if we have this one of these two conditions, then we use t distribution. So this is when sigma is unknown. This is when sigma is unknown. Okay, if sigma is unknown, so you look at this. So if one of them is met, if you find one of them in the population or in the sample, then we use the so-called t distribution. Now, the t distribution is more or less, it looks like a normal curve. It's very similar. And for normal curves, if suppose this is a normal curve, now we have a lot of we have different normal curves, and all of them, they are characterized by mu, the mean, where they are centered at. The mean tells us the center of the curve, and this wideness or this the variability is represented by sigma. So to differentiate a normal curve, we use these two characteristics or parameters. And based on this one, we can have different, if I change sigma, for example, with the same mean, I can have a more wider curve. If I decrease this one, we will have more narrower curve with the same center. If I change sigma with the same, if I change mu with the same sigma, we will have a shifted curve, either this way or that way, but the same shape because sigma is unchanged. So the normal curves are characterized by these two parameters. However, the t distribution, we don't need this one, or we don't have this one. Actually, we do have them, but those will come later. Okay, so for the t distribution, it is characterized by a so-called degrees of freedom. Okay, we will introduce this degrees of freedom for t distribution. Of course, we didn't need this one for normal distribution, but for t distribution, we need the degrees of freedom. For example, t distribution with 1 degree of freedom will look like different. With 2 different degrees of freedom will look like different, and so on and so forth. So the center doesn't change. For all this, with different degrees of freedom, the center doesn't change. It's always around 0. It's centered around 0. Okay. The question is the curvature, the wideness. So as this degrees of freedom increases, this shape of the curve looks more like the normal. It approaches this normal curve. And I will show you what I mean by this one. But first, let me explain a bit, give you an idea, because the degrees of freedom, always it's kind of difficult to understand at the beginning. So let me give you this idea, not in terms of a distribution, but I will try to explain it in a different way so that you can have an idea what it means. Now, suppose we have 3 numbers, and when we add them, suppose they are positive numbers. So when we add them, let's say they give us 10. Okay. Now, if, well, this is an equation with 3 variables. Now, if I give you, well, first, can we solve this equation? The answer is no. I cannot know the values of x, y, z, because I can have different values, different combinations of numbers that give me 10. How about if I give you the value of x? Let's say x is 4. Okay. How about now? So at this point, we cannot solve x, y, z. We cannot find the values of x, y, z. And let's say we have, I gave you one value. Well, this is just not x. Now I give you one value. The first variable is 4. Can we find this too? Still, it's no. I will write it. We cannot determine what the values of y and z are. It's not unique because, for example, I can have this is 4, then we have 6. So we can have 3 and 3. We can have 2 and 4. What else do we have? We can have 5 and 1, and so on. So, or vice versa. So the solution of this one is not unique. Okay. Now, how about this is 4. This is, let's say, this is 5, and this is z. How about now? Can we determine the value of z? Well, definitely yes. Now, this is what we call degrees of freedom. In order to determine the exact value or the unique value of this one, or the values of x, y, z, you need to know n minus 1 of them. N is the number of variables in the equation. So if I give you the value of n minus 1 of the variables, then you can determine the value of the remaining one variable. And that variable will be unique. It's not going to be different. It doesn't take different values. But if you remember, I mean, here, for the first case, we can have different combination. It's not unique. Values of x, y, z, they cannot be unique. Because I can just put some numbers that gives me 10. And those will be different combinations. Even here, the same. But when n minus 1 of the variables are known, in this case 3 minus 1, which is 2, when 2 of them are known, then I can have a unique solution to this equation. Okay, and that's what we mean by degrees of freedom. So this one, it does have n minus 1 degrees of freedom. Okay, so this is just to give you an idea what we mean by this, and similar thing applies here. Okay, don't interpret it the same way, but I hope this will give you an idea what we mean by degrees of freedom. Okay, therefore, when n minus 1 is of the variables are known, we can find a unique solution to this one, and this has a somehow similar idea about distribution of about the t distribution. All right, now, and one thing that I would like to do here is I will show you how to find critical value using t distribution, but before that, let's look at the properties of. Okay, the degrees of freedom is given by this one always, by the way. It's given by n minus 1. Okay, so where n is the sample size. The t distribution corresponding to any particular degrees of freedom is bell-shaped and centered at 0. Just like the standard distribution, the standard normal distribution. So the center is always at 0 and still it's bell-shaped. Okay, so it's very similar to the normal standard normal distribution. Every t distribution has greater variability than the standard normal distribution. So this is the difference. Every t distribution has greater variability than the standard normal distribution. So if we assume this to be, well, it's not a good graph, but let's say this is the normal standard normal distribution. So the t distribution will be more kind of wider because it has more variability. So here you expect it to be kind of wider. So every t distribution has greater variability than the normal distribution. As the number of degrees of freedom increases, as this number increases, degrees of freedom increase means n increase, the sample size is increasing, okay? So when the degrees of freedom increases, the variability of the corresponding t distribution decreases, which means this blue curve gets kind of shrink, which means it's approaching the red curve. And as the number of degrees of freedom increase, the corresponding sequence of t distributions approach the standard normal distribution. It will approximately be like the normal distribution. So as n gets bigger and bigger and bigger, we will have the same like the normal standard normal distribution. And here I put this graph so that you can see what I mean by this. So here we have t distribution with degrees of freedom equals to 2. This is this color. If you see here, it's less peaked. It's the height of this one is lower than the rest, but here it's wider. If you here look at this one, it's on top. So it's wider, that means. T distribution with degrees of freedom 4 is the red one next to it. So here it's getting higher now, it's going up. And here it's going down, it's below the first curve. And if you increase degrees of freedom to 8, you have the green curve. And well, as you can see, it's approaching the yellow curve, which is the standard normal. So if you keep increasing this one, it will approach the yellow curve. And that's what we mean by those properties. Okay, so before I go to this one, let me go and show you what this looks like in practical and how we can find the t distribution. So here we have the technology, the salt, using the salt, which is from the WebAssign. And we have been using this one to find values for a normal distribution. Here you can choose the normal t distribution f chi-square. We haven't learned this one, so for now, just t distribution. Here it will ask you degrees of freedom. So the only parameter here is the degrees of freedom. We don't need mu, we don't need sigma, just degrees of freedom. Now let's start with 0. that doesn't work. We need to have at least 1 degree of freedom. Now, if you have 1 degree of freedom, look at this graph now. It doesn't even look like a normal curve, not even close, but still it's bell-shaped and it's centered around 0. And it's still bell-shaped, of course, it's symmetric. It doesn't matter what shape it is, but it's symmetric. How about if we make it 2? Well, a bit better. 3, 4, 5, 6, oops, 7, 8, 9. Here the difference is not much. 10, and so on. And as you see here, if you remember, for a standard normal distribution, this shaded area, if it is 0.05, okay, this Z critical value is -1.645. Let me go to normal and the same 0 and 1, and look at this one. This is, if you round to 3 digits, it's -1.645. Okay. Now, if this shaded area to the left is 0.05, I'm not changing this one. We are trying to find this value. Okay. So for Z, it's this value. How about for T? With 10 degrees of freedom, it's -1.8. It's even lower than the Z critical value. How about if I increase it to, let's say, 20? What do we get? It's going up, right? -1.7. It was -1.8. How about if we go to 30? Much closer. How about 100? -1.66. It's approaching. How about 200 degrees of freedom? -1.6, almost close. 500. Well, almost, right? So what I'm trying to say to show you here is, as the degrees of freedom increases, the curve, the T distribution, is more like a normal distribution, standard normal distribution. Okay, don't look at this shape. This shape is because we have aligned this one. That's why it's kind of getting shrink, because it's magnified. Okay, just to show us this area. This yellow is the shaded area that represent this 0.05. So because of that, this curve is shrinking. It doesn't mean the shape of the curve is like this one. Okay. All right. Going back. So this is how we can find the critical value for using T distribution, or from T distribution. And of course, we have the right tail, post tails, and so on, just like the normal distribution. Okay. And since it's symmetric, this on the left and on the right, they will be the same. Okay. Still, we have the symmetry. And another way is using the table. I will post this one on Blackboard. I haven't posted it yet. And here, let's say, for example, you are given a 95 degrees of confidence interval, confidence level. This is the confidence level, 95%. And this is the area in between the two critical values, the negative and the positive. Okay. Now, for different degrees of freedom, you will have different values. If degrees of freedom is 1, then the critical value is 12. Okay. Let me go back to this one. 95, this has to be 25. You see, 12.7. What do we have here? 12.71, 12 points, of course, 71. If you round the 6 to the left, it will be 12.71. So that's for degrees of freedom 1. And as you increase the degrees of freedom, the values decrease. From going from 1 to 2, it changed by almost 3 times. Okay, then we go down, we increase the degrees of freedom. So the problem with this, using this table, is at some point it starts jumping. For example, from here, we jump to 40, and then 60, and then to 120. And from that one onwards, if the degrees of freedom is above 120, we can use the values for standard normal distribution. These are the values for standard normal distribution. If you remember, this is the value. This is another value from the standard normal distribution. And these are the rest, okay? So if we have values above this one, we use these critical values. Okay. All right, going back to a one sample t confidence interval for mu now. So we know how to find the critical value, t critical value. So using the sample standard deviation to estimate the population standard deviation, of course, and replacing the z critical value by t critical value, the formula becomes x bar plus or minus t critical value. We just replace this one. We only replace this one by t. It was z originally, and replace the sigma by s. So we get this formula. So there are two conditions that we need to check here. One is, of course, the sample size. It has to be greater than 30 because in that case, if it is greater than 30, using the central limit theorem, we have the guarantee that the distribution of the mean x bar is approximately normal. If this is not true, if it is not greater than 30, we need to have the population distribution to be normal, approximately normal. We need to know that this is normal. Otherwise, I cannot use this type of inference. And the second condition is the randomness of the sample. The sample has to be random, or it has to be representative to the population. This, we had it before. Okay, both of them we had them, but here it becomes a bit different. N has to be greater than 30, but previously we would say p times n and 1 minus p times n, they have to be greater than 10. All right, so when these conditions are met, we have this formula to find the confidence interval. And to find the degrees of freedom, it's just n minus 1, and the critical value, to find the critical value, use these degrees of freedom and use the table or the technology. And once you have them, you can just construct the confidence interval, and the interpretation is the same like what we had before, what we learned before. Okay, now let's look at this example now. I will just jump here. We have n equals to 38, x bar we have 28 minutes, and s sample standard deviation to be 1.57 minutes. The researchers were interested in estimating the mean processing time for flu patients using the drive-through model. Okay, so this is they were trying to study this one, and they did some survey. You can pause this one and read it if you want. So in order to have an idea or to estimate this mean processing time, they have to collect some sample, and they collect 38 patients with mean 26 mean waiting time and standard deviation 1.57. Now, first we check the conditions. To make inference, always we check the conditions first. And the two conditions are, one is n has to be greater than 30, which is true in this case. And the other one is we need a representative sample or random, simple random sample. So since the sample is large, we don't need to worry about whether the population distribution is approximately normal or not. And the second condition is the sample has to be random. And here the 38 flu cases were randomly selected from the population of all flu cases seen at the emergency room. Does it tell here? Yeah, it's here. Selected at random. So since we have this one, then both the conditions are met. So we jump to the calculation. Now we have n to be 38, x bar is 26, s is 1.57, degrees of freedom 38 minus 1, which is 37. So the approximate TD critical value, let's go and find it ourselves. So this will be 37, and the critical value is 2.0262. So you can ignore the negative, or you can change this one to the right just to take the positive value. Okay, we don't, just for simplicity, you don't need the negative, because the reason is, see this one, since you have this plus or minus, being this number negative or positive doesn't make any difference, because plus negative 2.02 is the same with negative 2.02, and minus 2.02 is positive 2.02. So you will still have plus or minus. Okay, whether you pick the negative or the positive, it doesn't really matter. You will still have these two. So just for simplicity, we take the positive value, not the negative. Otherwise, there is no change other than the simplicity. All right, so this is the critical value, 2.02. Here we have the standard deviation of x bar, and then the so here we have the confidence interval. So we are 95% confident. So here we have the confidence interval, the interpretation. You can be 95% confident that the actual mean processing time for emergency room flu cases using the new drive-through model is between 25.9 and 26.51 minutes. So this is how we put it into the context of the question. Okay. Now the next that goes with confidence interval is the margin of error, as well as the sample size. So this is important because when we do surveys, we almost, not always, but we would like sometimes to have an idea about our margin of error, or to fix our margin of error. We don't want to have too big margin of error to make too big margin of error in order to be more precise. And well, the margin of error was given by 1.96 previously for 95% confidence interval, sigma over root n. This was for when we used the z critical value. All right, so the margin of error associated with a statistic was defined earlier as the maximum likelihood, maximum likely estimation error expected when the statistic is used as an estimator. Okay, so this is the maximum likely estimation error. When x bar is from a large random sample, is used to estimate a population mean, mu, the approximate margin of error is given by this one. Okay, and when we don't know sigma, we approximate this by this one. Then this means it will be unusual for the sample mean to differ from the actual value of the population mean by more than the margin of error. If we get the sample mean that differs from the population mean by more than the margin of error, then that would be an unusual case. So before collecting any data, an investigator may wish to determine the sample size required to achieve a particular margin of error, m. Okay, so in order to achieve m, in order to achieve some predetermined margin of error, you just have the only option to change n. By changing n, you can increase or decrease the sample of the margin of error, because we cannot change this one. This is based on the confidence level, based on 95%. Okay, So we cannot change that one. So the sample size required to determine a population mean mu with a specific margin of error m is given by n equals to 1.96 times sigma over m the whole square. Okay. And this is just by solving the margin of error m is 1.96 sigma over root n. So if you solve this one, you get this equation. So when we don't know sigma, there are cases that we use the range, where the range is just the maximum minus the minimum. And you divide it by 4, and you can use this one as an estimate of the population standard deviation, just like S. So here, in order to achieve a smaller margin of error, as you can see, the N and M, they have inverse relationship. So when you increase N, if N goes up, this guy will go down. Okay, the margin of error will decrease, and that's what we want. And as N goes down, M goes up. This will increase. And another thing is, as N increases, this one increases, the variance. And well, this is the estimate that I mean, because this is fixed. Okay, if we have the population that's fixed, it's not a variable. Okay, but if we have a variable, then that will be inverse. Okay. Okay. Now suppose we have sigma equals 100 and m equals 20, then n equals to 1.96 over sigma times sigma over m squared. And well, if we multiply this one, we get 9.8, which is, if we square this one, is 96.04. And rounding this up, we get n equals to 97 or larger is recommended in order to achieve that margin of error. Okay, the margin of error is this one. Okay. All right. So this is all about this lecture, and in the next lectures we will see how to perform a hypothesis test. Well, in the coming lectures in general, hypothesis test about population mean and about difference of two population means. So see you in the next lecture.